My name is Anshul Joon, BSc Chemistry Honors final year. Today we will read Pradeep's Physical Chemistry Volume 3 by Dr. S.C. Khetrapal, Raman Spectroscopy. 3.35. It is a special type of spectroscopy which deals with the absorption of electronic radiation but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with monochromatic light of a definite frequency mu, a small fraction of the light is scattered. Railing is found that if the scattered light is observed at the right angle to the direction of the incident light, the scattered light is found to have the same frequency as that of incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, solid, is irradiated with monochromatic light of a definite frequency mu, the light scattered at the right angles to the incident light contained lines only of the incident frequency but also of lower frequency and sometimes higher as well. The lines with lower frequency are called stroke lines, whereas lines with higher frequency are called anti-stroke line. The Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was the constant depending upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If mu I is the frequency of the incident light and mu s is the particular scattered line, the difference delta V is equals to I minus V is called Raman frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristic of that substance. The various observations thus made by Raman constitute what is called as Raman effect, and the spectrum observed is called as Raman spectrum. Thus, in a simple way, Raman spectrum may be represented as shown in figure 3.29. 3.36 Explanation for observing Rayleigh line and Raman lines. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return to the same energy, thus the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering or Rayleigh lines. However, if the collision is inelastic, still the law of conservation of energy will hold good. That is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and hence the lower frequency than that of the incident photon. This explains the occurrence of Stokes line. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than of the incident light. This explains the occurrence of anti-Stokes line. This explanation may further be elaborated as follows. When the photons strike the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most cases, the excited molecule does not return to the original level. It may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of stroke lines. Thus, a part of the energy incident photon remain absorbed by the molecule so that the molecule has high energy than before. Alternatively, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes line. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown in figure 3.30. Levels have been shown equally spaced for the sake of convenience. 3.37 Polarizability of molecules and Raman spectra. The Raman effect arises on account of the polarization distortion of the electronic cloud of the scattering molecule, and that is caused by the electric vector of the electromagnetic radiation. The induced dipole moment mu depends on the strength of the electric field E and nature of the molecule. We write mu is equals to alpha E, equation 1. where the quantity alpha depends on the nature of the molecule and is called polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of atoms or spherically symmetrical molecules such as CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecule. In case of all diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, non-spherical rotors, the polarizability depends on the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. We write alpha parallel is greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Type of molecule showing Raman spectra, rotational Raman spectra. A molecule scattering light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectrum is that polarizability of the molecule must be anisotropic. That is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all the diatomic molecules, linear molecules, and non-spherical molecules give Raman spectra. That is, they are rotationally Raman active. On the other hand, spherically symmetrical molecules such as CH4, SF6, etc., do not give rotational Raman spectrum. That is, they are rotationally Raman inactive. These molecules are rotationally microwave inactive. In fact, this is one of the reasons for importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas further the former only require the polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibrational rotation. It is sum of two parts. First, equilibrium polarizability alpha naught, that is the polarizability of when the atom of the molecules are in the equilibrium position. Second, the sum of the polarizability of the molecule due to the various rotational and vibrational motions, each term depending upon the frequency of rotation or vibration. Thus, alpha is equals to alpha naught plus summation of delta alpha n delta r into r n cos 2 pi v n t, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atom involved. Further, the electric vector of the electromagnetic radiation varies with time in a sinusoidal manner as E is equals to E naught cos 2 pi V naught t. Substituting the value of alpha and E from equation 2 and 3, in equation 1 we get mu is equals to E naught alpha naught cos 2 pi V naught t plus summation of delta alpha n into Rn cos 2 pi V n t cos 2 pi V naught t is equals to E naught alpha naught cos 2 pi V naught t plus half E naught summation of delta n naught by R into Rn cos 2 pi V naught minus V n t plus cos 2 pi V naught plus V n t. Cos A cos B is equals to half cos A plus B plus cos A minus B. This expression consists of three terms. First term has the frequency of the incident radiation and represents the Rayleigh scattering. The second term consists V naught minus V and represents Stokes line, and the third term contains V naught plus V and representing the NT Stokes lines. This expression consists of three terms. First term has the frequency of the 3.38 Quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are delta J is equals to 0 plus minus 2. The selection rule delta J is equals to 0 corresponds to the Rayleigh scattering, whereas selection rule plus minus 2 gives rise to the Raman lines as explained below. We know that the energy of the rotational level in terms of the wave number with quantum number j is given by bar is equals to bj into j plus 1. When transition takes place from a lower rotational level with quantum number j to a higher rotational level with quantum j dash, the energy absorbed in the terminal number given by delta v bar is equals to vj dash into j dash plus 1 minus vj into j plus 1. For selection rule, delta j is equals to plus 2, that is j dash minus j is equals to 2 or j dash is equals to j plus 2. We get is equals to b j plus 2 plus j plus 3 minus bj into j plus 1, b into 4j plus 6, whereas j is equals to 0, 1, 2, 3. Again, for selection rule, delta j is equals to minus 2, that is j dash minus j is equals to minus 2 or j is equals to j dash plus 2. We get bj dash into j dash plus 1 minus b into j dash plus 2 j dash plus 3 is equals to minus b for j dash plus 6, where j dash is equals to 0, 1, 2, 3. Combining the results of the equation, the wave number of the lines obtained in the Raman spectrum will be given by v bar is equals to vi plus minus delta v bar. V bar is equals to vi bar plus minus b into 4j plus 6, where j is equals to 0, 1, 2, 3. Here vi represent the wave number of the railing line, plus sign gives line with higher wave number called anti-Stokes line, and minus sign gave line with the lower wave number called Stokes lines. From equation 5, it may be seen that j is equals to 0, v bar is equals to vi bar plus minus 6v, that is the first Stokes and anti-Stokes line will be at separation 6v from the railing line. Further putting j is equals to 1, 2, 3, the separation between any two adjacent Stokes line or anti-Stokes line will be 4b. Thus, pure rotational Raman spectrum expected for a diatomic molecule may be represented in figure 3.32. Intensity of the pure rotational Raman spectra. As explained earlier, intensity of the lines depends upon the population of the initial level from where the molecules are excited or de-excited to the final level. Since the population of the rotational energy level is shown in figure 3.20, therefore the intensity of the Stokes and anti-Stokes line varies in a similar manner. 3.40 Application of pure rotational Raman spectra. From the pure rotational Raman spectra, nothing the separation between the line, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecule can be calculated, as explained earlier. 3.41 Quantum theory of rotational vibrational Raman spectra of diatomic molecule. For large molecules, the line obtained due to rotational transition are so weak that they are beyond resolution. Hence, we have pure vibrational Raman spectra for which the selection rules are same as for the pure vibrational spectra discussed earlier. Delta V is equals to plus minus 1, plus minus 2, and so on. However, in the case of diatomic gaseous molecules, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecules give rotational vibrational Raman spectra, which can be explained as follows. The selection rules for the transition are: delta V is equals to plus minus 1, delta J is equals to 0 plus minus 2. However, at room temperature, the most molecules are in the lowest fundamental level, vibrational level, V is equals to 0. Therefore, the significant vibrational transition from V is equals to 0 to V is equals to 1, called the fundamental vibration transistor. Restricting ourselves to the vibration transition only, the results obtained are as follows. For delta J is equals to 0, delta V bar is equals to omega E into 1 minus 2xe called Q branch. for delta j plus 2, delta v bar is equals to omega e 1 minus 2xe plus b into 4j plus 6, called S branch. For delta j is equals to minus 2, the v bar is equals to omega e 1 minus 2xe minus b into 4j dash plus 6, called O branch. Representing the values for Q, S and O branches by delta V bar Q, delta V bar S and delta V bar O respectively, then the wave number of the exciting radiation by Vi bar, the wave number of the Stokes line will be as follows. V bar Q is equals to Vi bar minus V bar Q, Vs bar is equals to V bar I bar minus delta V bar S. V bar O is equals to V bar I minus delta V bar O. We have considered the case delta V is equals to plus 1, which represents Stokes line. The anti-Stokes line are those for which delta V is equals to minus 1. They are usually weak because very few molecules are in the excited vibrational state initially. The rotational transition accompanying the vibrational and transition from V is equals to 0 to V is equals to 1, and the rotational vibrational Raman spectrum obtained may be represented in figure 3.32. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. First, since Raman frequency are independent of the frequency of the incident radiation, hence by suitably adjusting the frequencies of the incident radiation, Raman spectra can be obtained in the visible suitable adjusting the frequency of the incident radiation. Raman spectra can be obtained in the visible spectrum range where they can be easily observed rather than more difficult infrared range. Second, Raman spectra can be obtained even for molecules such as O2, N2, Cl2 where no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Third, Raman spectra can be obtained not only for gaseous but also for liquid and solid, whereas infrared spectra for liquid and solid are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecule structure of a large number of compounds have been determined by Raman spectroscopy. However, infrared still continues to remain popular. 3.43 Experimental arrangement for Raman spectra. The experimental arrangement for observing Raman spectra is shown in figure 3.3. The fraction of the light scattered is so low that normally weak Raman lines are observed. Hence, to detect these lines, it is necessary to use powerful sources of incident line. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of wavelength 4358 Armstrong, that is 435.8 nanometer. However, with the development of laser, which are very powerful source of monochromatic radiation, Raman spectroscopy has been greatly revolutionized. This was it for the Raman spectroscopy. Thank you.